All right, everybody, welcome back to Net 125. This is John Armke. Today we're going to be going over Module 3, Protocols and Models. So let's take a look at our objectives for today. We're going to look at the rules. All protocols are sets of rules for communication. And we have different things that group together into what we call protocol suites, allowing protocols to work in sequence so we can subdivide their functions. We also have some standard organizations we're going to talk about today, different groups around the globe that help to define the ways in which certain items should behave so that we can make sure that we are establishing strong interoperability. That lends itself to what we call structural reference models. These reference models allow us to determine when trying to improve a standard or possibly create a deviation that might allow a niche version to emerge. We can make sure that the transition between layers is sufficiently separated so that we can pass things from one layer to the next. Data encapsulation, we're going to talk about how data is transported across a network, how it is encased in layers of data to be able to pass information up or down securely across several different platforms, what we call platform agnostic behavior. And then we'll talk about data access, how local hosts access local resources on a local network. Tired of the word local yet? Buckle in. So let's look at section 3.1, the rules. I really wanted to make a fairly Odd Parents reference here, but feared it would just make me look old. So communication fundamentals. Networks can vary in size and complexity. It's not enough to have a connection. Devices have to agree on how they're going to communicate. Now there's three elements to any communication structure. We have to have a source, we have to have a destination, and we have to have a channel to provide a path of communication to go between. In other words, we have to have a sender, a receiver, and a medium. Media is the plural there of communication. We have to have a way to get it from A to B. So all communications are governed by protocols. These rules that set up the communication will vary depending on what protocol is being used. So for example, the big two that we talk about for transport is either TCP or UDP. TCP deals with connection-oriented protocols, UDP deals with non-connection oriented protocol. So here we have a graphic of two people on the left, and they are trying to speak to one another. You know, somebody's trying to maybe ask where a restaurant is, or excuse me, have you seen my friend? I'm trying to meet somebody, or do you have the time? You know, any number of various pieces of chit chat. And we have different ways that we like to initiate conversation. There's a lot of study going on now that in an increasingly disconnected society where we live inside of our own heads dealing with smartphones and screens and things like that, are we losing the ability to read the cues that allow us to initiate communication successfully? Are we modifying our protocols to a point where they're no longer functional? If we look at a computer in same comparison, we see that there's two nodes or two hosts trying to transition a message. And we have to follow the same pattern. The message originates, has a transmitter path, goes over the medium, has a receiver path, and then is decrypted at its destination. So individuals have to use established rules to govern communication. Doing things spontaneously can be very difficult. Human beings love novelty, but this can be something that is very off-putting because if you're having to struggle to understand basic communication, it can be very difficult. Excuse me. There has been a lot of discussion that if we were to meet an extraterrestrial species that is of the same intelligence level as our own, or within range, one of the only ways we could be sure to be able to communicate is the nature of music and mathematics, because human speech, as said by Tommy Lee Jones in Men in Black, is so primitive, it's looked on by some of the higher level cultures as a form of infectious disease. And that is not to say that we are not following rules, it's just the broadness of those rules and the broadness of our levels of communication to convey the same thing. A common phrase that I hear talking about whenever I was learning a foreign language when I was in grade school, up until now, trying to learn, refresh myself on my German or French. There are words that exist in different languages that express very distinct feelings. The term Schadenfreude in German, shameful joy, refers to a very precise feeling, but we have to have something that is descriptive in 2 or 3 words rather than just 1 word. And it's the nature of a global society where we learn and borrow from one another. If we look at the 2 messages on the right on this slide, you see where it says humans communication between governed rules. It is very difficult to understand messages that are not correctly formatted and do not follow the established rules and protocols. A estrutura de gramática de lengua de Pontucayo e dos sentence faz a configuração humana é compreensível por muitos indivíduos diferentes. So I'm thinking it slips into Portuguese in the second half. I'm just guessing because that doesn't read entirely like Spanish, but it's close. Now, if we look at the bottom one, it says rules govern communication between humans. It is very difficult to understand messages that are not correctly formatted and do not follow the established rules and protocols. The structure of the grammar, the language, the punctuation, and the sentence make the configuration humanly understandable for many different individuals. And that's something that is difficult for a lot of people is just finding equivalencies. Like in German, I keep falling back on German, but it's because German is very literal about a lot of things. Gloves are, they're called hand shoes. That's the literal translation. So, instead of saying, gloves as a separate word, we just say, we already have shoes, we'll just modify it to go on hands. And I believe it's water shield frog for a turtle. So it's Wasserschild. Goodness, I can't remember the word for frog. But the idea is that we're borrowing these words to move something together to describe something. So if you hear hippopotamus, I believe that means river horse or water horse. So again, taking descriptives to put them together. And that's how protocols tend to work. We look at that in English or in modern languages that we use all the time, like Spanish or French or what have you. And it's something that's not too far off from what we do with computers. We have to take something we already know works and refine it to work for a different purpose. So protocols have to account for identified senders and receivers, common language and grammar, speed and timing of delivery. If I were speaking as fast as I could, or was speaking exceptionally slowly, it would make it very hard for you to understand if you were anticipating a particular speed. Confirmation or acknowledgement of requirements, that is going to be dependent on what protocol we're using. We have to say, are we going to bother with connection oriented at all? If we're using UDP, I don't care if you got my message, I sent it. I did what I was supposed to do. With TCP, however, it's like, okay, I'm going to send the message. Here's the message. Did you get the message? Was it in the correct order? Common computer protocols have to be in agreement for message formatting, encapsulation, encoding, size, transmission timing, and delivery options. So here we see, excuse me, on the left-hand side, the process of converting information into an acceptable form for transmission. So we have the message source. Now, instead of just having a transmitter and receiver on either side of the medium, we have now added an encoder and decoder. Decoding is exactly the same as encoding, it's just done in reverse. So encapsulation and decapsulation, same idea. Whenever we do something, we have to be able to reverse it on the opposite side. That's the process of having a structured reference model. We pass it down one way to have it set up for transmission. Once it's received at the other side, it has to be peeled apart to be able to be interpreted. So message formats depend on the type of message and the channel used to deliver it. What we see here on the right is a comparison between an IP packet and a letter being sent via the US mail service. So it just kind of depends on how the message is being sent, what type of container we need. Do we need to attach postage? Is the sender and return address correctly formatted? Is it sealed? Is the message going to break open and fall apart? Fragmentation, if you will. Now, encoding between hosts must be in an appropriate format for the medium, which means that if we're going to send things across a network as a packet of information or a frame, we have to make sure that it's converted into bits, because bits are the only way that we know how to transmit things in an analog capacity so that they can move across electrical lines, or they can move across radio frequency, or they can move across fiber optics. Once it gets back, it can be converted back into a digital form. So once we send something, we have to make sure that it's the right size, the right language, if you will, and transmit it over the right type of medium. Message timing deals with three primary items: flow control, response timeout, and the access method. Flow control just basically means that we're trying to make sure that you're getting the information that you need and not wasting a ton of transmission time. Imagine that you went to a restaurant and you had a glass of water on your table. If your wait person were to come to your table and try and refill your water, what would happen if they weren't paying attention to how much water they were pouring or how fast? The glass would eventually overflow and it starts spilling, and it would not only waste water but probably cause some kerfuffle because your trousers might get wet or what have you. So flow control is an observational technique that's done at the transmission level to see, are we getting it in the cup, if you will? Is the cup full? Are we pouring it too quickly to where when we try and stop, everything's going to slosh? Or if we're pouring something that's carbonated, is it going to get all frothy and then go flat? Flow control helps us to mitigate that. Response timeout discusses how long it takes for a device to say, okay, I've been waiting for a transmission to come through, it's not coming, let me go ahead and knock the timeout and retry the connection. Or if I've retried it several times, let me go ahead and submit a message to my user saying, hey, we've been trying to get this working, it's not going through, let's try something else. And then the access method. This determines when someone can actually send a message. Now there's a couple of different things we'll talk about, which is carrier sense multiple access, and there's collision detection and collision prevention that's put out there. Or collision access. There was a collision avoidance and collision detection, CA and CD. A lot of alphabet soup in this type of business. So these rules in the protocol tell us when a collision occurs, what happens. Now, collisions are just where messages kind of overlap one another. The messages start messing with one another and become corrupt because the signals are no longer the original transmission. Some protocols are proactive, like CSMACD, and then there's one that tries to, that's CA, I'm sorry, collision avoidance tries to be proactive. Reactive stuff is collision detection and says, hey, this happened, let's go ahead and see if we can fix it. So message delivery can follow one of three primary methods: unicast, multicast, and broadcast. Now you'll notice on the right hand side we have three graphics. Unicast says we're going from a source to a single host. Multicast says we're going from one to many hosts, but not all of them typically. And then broadcast is we're connecting to everyone. Now broadcasts are used in IPv4, but they're not used in IPv6, and we'll talk about why later on. So we see here that we've got just kind of a node icon instead of showing a particular device. The node just shows different delivery options, so we see that we don't worry about whether or not it's a computer or a printer or anything else that's dealing with the signals. We just see that we have an origination point shown in kind of a reddish orange. Then we have the green for the recipients and the yellow for the non-recipients. So now we can take a look at protocols 3.2. Protocols can be implemented on devices in hardware, software, or both. Protocols have three primary characteristics: function, format, and rules. So network communications protocols will enable two or more devices to speak over one or more networks. Security protocols deal with authentication, integrity, and encryption, also known as the CIA triad: confidentiality, integrity, and availability. Routing protocols deal with exchanging route information, trying to path the transition route, if you will, from one router to the next, or from one switch to a router, etc., finding the best way to get from one computer to the next. The internet is based on the routing system being able to go from one computer to another in a global configuration. Discovery protocols are used for the automatic detection of services or devices being added to or removed from a network dynamically. So whenever we plug in a new laptop, or if we plug in a printer, that device should be discoverable given a certain level of configuration. Now, devices use agreed upon protocols to communicate, and protocols can be multifunction. So in the graphic on the left, we see an end user transmitting a message using IPv4. That means the network encodes it using an IPv4 header. That header is transmitted to a router which can understand that message, And then once the routing is finished and it passes across whatever path is necessary to get to its destination, that message can then be decrypted because the server at the other end, whatever it may be, is able to understand IPv4. Now, just because it can understand the message doesn't mean necessarily it'll understand the payload, but it does mean that everything will be processed correctly as far as network transmission is concerned. So addressing will identify who sent it and where it's going. Reliability provides guaranteed delivery. That's a TCP item. Flow control, we talked about a little bit earlier. Sequencing allows us to label transmitted data fragments to make sure they make it in the correct order. Think about a jigsaw puzzle. Putting together a jigsaw puzzle for most people requires identifying little visual tags, patterns, and continuations that allow us to say, hey, this particular piece should go right around here. There's a big green patch over here representing maybe a tree or a football jersey or who knows. So I'm going to put all these green pieces together and hopefully I can fit the edges together and test them out and see which one goes where. What if, on the other hand, somebody had already completed the puzzle and on the back of each piece had written a code number? So let's say that all of the columns were letters and all of the rows were numeric. So you had column A, piece 1, A1, and then you had A2, A3, and they basically had mapped the entire puzzle. You could actually complete the puzzle upside down with none of the visual cues because you had the sequence numbers. Now this is anticipating that the sequence number that that person chose to use made sense. Error detection. This is going to detect data corruption via transmission. So this is going to find out when something's being sent, if there is data that is being damaged or lost, and try and correct it in flow, if you will, in vivo, if we were talking about medical work. Application interface. This function deals with process-to-process communications. So if we're trying to identify a direct connection between two applications, this is the type of service and protocol we would employ. Protocol interaction deals with how each protocol has its own function and format to handle different aspects of transmission from one place to another. So for example here, we have a packet being sent from a laptop into the internet to go to a server. HTTP, TCP, IP, and Ethernet transmission are all involved as part of the process. HTTP, or Hypertext Transfer Protocol, governs how web servers and clients interact, and it defines our content and format for transmission. Transmission Control Protocol deals with individual conversations between hosts, flow control, and provides guaranteed delivery through sequence numbers and verification checks. Internet Protocol deals with how to send things globally from one sender to one receiver, or multiple receivers in the case of multicast or broadcast. Ethernet deals with the physical definitions of moving things from one NIC to another on the same LAN. So once something gets to the same local network as its destination, it is then able to rely on Ethernet protocol for locations rather than having to go through the routing protocol at IP level. Protocol suites 3.3 deals with groups of protocols that are working in conjunction with one another. Now, this set of rules, when combined together, helps us to solve a problem. Here we have the similar an analog to the question in the beginning when we were first talking about the commonalities between human conversation and that of a machine. Content layer says, I want to know where the cafe is. So the content of my message is, where is the cafe? The protocol suite for a human conversation, the rules, deals with use a common language, wait for your turn, and signal when finished. Now, common language here is going to be English. It could be any number of things, or you could hope that the language that you are speaking is interpretable by the other individual involved. The person right there on the left in the red shirt has their hand up to their ear. It looks like they may be on the phone. So if somebody is going to interrupt their day and try and request that information, we have to be sure that they're not in the middle of something first. We start disrupting another conversation. We have to make sure we have segmentation at that point. And then once we're done with our request, we have to signal when finished, which usually means taking a breath or a pause, or you can hear the lilt at the end of a question. Where's the cafe? That up tilt says that there's a punctuation there that is anticipating a response. Now, protocols have to be viewed in terms of hierarchy, higher and lower layers. Higher layers deal with being able to do more complex tasks. The actual content of the message is considered higher layer because communicating that message is more fundamental than actually interpreting it once it's been moved. Lower layers are dealing with moving data and then providing services to the upper layers. So the physical layer of transmission, just making, a sound with your voice box to make a word, is much more simplistic than dealing with being able to elucidate a question clearly, concisely, and in the correct language. Now, there are several different protocol suites out there. One of the most common ones that we deal with and constantly talk about is IP combined with TCP or TCP/IP. So Internet Protocol and Transmission Control Protocol. This is maintained by a group called the Engineering Task Force, Internet Engineering Task Force, or IETF. Open Systems Interconnection Protocols, or OSI, is developed by the International Organization for Standardization. It's based in France, so I believe that it's International Standardization Organization, but of course, different terms, close to it. As well as the ITU, or International Telecommunications Union. AppleTalk is a proprietary suite that is released by Apple Incorporated. Apple loves to have proprietary stuff. And then Novell NetWare does the same thing, proprietary suite developed by Novell Incorporated. You can see at the 4 primary layers that we talk about for TCP/IP, application transport, internet, and network access, that there are analogs within each of these 4 protocol suites that we deal with. Now, TCP/IP is going to be what we handle for the purposes of this course. You may be in other courses in future where you deal with the stuff that's in ISO, AppleTalk, or Novell. Most TCP/IP protocols operate in a very limited space because these are focused on strictly interactions with the application, being able to transport things between networks, and transmission over the internet. The most common layer, access layer protocols for LANs are Ethernet and WLAN. So Ethernet is the physical cabling that we would do for fiber optic or copper, and then WLAN is our wireless LAN communication. TCP/IP is used by the internet as a whole and includes a number of different protocols. So if we take that previous slide and we go to TCP/IP, we can take those 4 layers of the TCP/IP model and break it down into a much larger selection of components. We see here that we've got in the application layer the name system, host configuration, email, file transfer, web and web services. We move down to transport and we can see connection oriented versus connectionless. The internet layer has IP versions 4 and 6 as well as NAT. Messaging has ICMP, Internet Control Message Protocol, versions 4 and 6, as well as version 6 ND. Then we have routing protocols. So Open Shortest Path First, or OSPF, External Internet Gateway Routing Protocol, or IGRIP, and then BGP, which I believe is Best Gateway Protocol. Now, TCP/IP is an open standard suite. Open standards mean that it's not proprietary. You don't have to pay an organization to be able to use it. And stuff that functions well and doesn't have an associated licensing cost tends to spread like wildfire because there's a lot to recommend it. That means there's going to be a lot of support because a lot of people are testing it. The best way to test anything is to have as many samples and test cases as possible. How do you do that? Make it free. Standards-based protocol suites that are endorsed by the networking industry and approved by standards organizations to ensure interoperability tend to be successful, and TCP/IP most definitely is that. So here we can see the process of encapsulating and sending something to a web client. When we go ahead and send the information to a client, it's already been encapsulated into bits. So if we look at the bottom string, we see that it's all 1s and 0s. And that 1 and 0 string can be broken up based on the headers into an Ethernet frame, an IP packet, a TCP segment, and then a user data payload. Once that information is received, the web browser can be de-encapsulated by reading the information out into the actual contents. Now, I mentioned earlier that we would talk about standards organizations, the people who are responsible for trying to standardize and maintain the interoperability of all of these protocols and protocol suites that we would use. We talked about the IETF briefly, the ISO. So open standards, of course, encourage interoperability, competition, and innovation. Standards organizations cannot be assigned to any one vendor. They have to be neutral. They have to be able to take a protocol and work with it and say, based on the merits of this protocol, we would recommend doing X, Y, or Z. If it doesn't work well, here's how we would improve it. So it's kind of a rising tide raises all ships kind of argument. Nonprofit organizations, of course, you don't want to run a standards organization for profit because that tends to color the opinion a little bit. That tends to make people seem that if you're working for profit, that you can be bought with enough donations, quote, end quote, to be able to turn your research one way or the other. Standards organizations are also established to develop and promote the concept of open standards. So they're kind of self-promoting in a way to say, this is how we do it, this is how we believe you should do it. So the IEEE, the IETF, the IANA, ICANN, ITU, and TIA. ICANN is responsible for your IP address numbers. IANA is a subsidiary of ICANN. The IEEE deals with electrical standards. The ISOC, or Internet Society, promotes the open development and evolution of Internet technologies. The IAB is a subsidiary that deals with architecture and development of Internet standards, as well as management. There's a split between the IETF and the IRTF. IETF deals with engineering. IRTF deals with research. So IETF deals with developing, maintaining, and updating current technologies, whereas the Research Task Force deals with long-term research and development on stuff that's coming in the future. You know, how do we deal with modifying the existing infrastructure to support IPv6 in a global community that has already taken time to accept IPv4. ICANN, as I said, is the parent company of IANA. I'm hesitant to say company, it's a standards organization. ICANN, Internet Corporation for Assigned Names and Numbers, coordinates the allocation of IP addresses, management of domain names or DNS services. IANA actually oversees and manages the allocation, passing them out to the Tier 1 ISPs and regional Internet registries, or RURs. The Institute of Electrical and Electronics Engineers, IEEE, deals with standards in not only telecommunications and networking, which we deal with, but power, energy, and healthcare. So IEEE is a fairly common standards organization, as is the ISO. The Electronic Industries Alliance, they deal with standards relating to electrical wiring, connectors, as well as the 19-inch racks used to mount networking equipment. So if you take a look at the 19-inch wide racks, just a little bit more than 1.5 feet, those are developed in concert with the EIA, so that internationally you can buy a rack-mounted object and it should bolt in without any major problems. TIA develops communication standards and radio equipment, cellular towers, voice over IP, satellite communications, and more. TIA EIA actually works together in order to standardize the RJ45 standard for Ethernet, for the 568A and B wiring standards. The International Telecommunications Union, or Telecommunications Standardization Sector, ITU-T, defines standards for Internet Protocol TV, video compression, broadband communications, and stuff that we deal with as far as our direct interfaces with these materials. So video compression would be things like the H.265 codec, which is already being upgraded to H.266 over the next few years. Section 3.5, reference models. So remember I talked about earlier how the reference models allow us to compare different structures based on whether or not we're talking about, in this case, TCP/IP or OSI. There are complex concepts involved in networking, and we have to have ways to be able to structure them in a layered format so that we can look at individual components rather than being overly stimulated or confused by the whole. OSI is much more detail-oriented, broken up into separate sublayers, simply because it has to apply to a number of different models for network operations, not just TCP/IP. So if we were looking at something for Novell or Apple, things like that, we would be much more in step with the OSI model to make sure we're separating all the protocols effectively. Now, the benefits of using a layered model are multifold. It assists in protocol design because we have to make sure that protocols that operate at one layer have defined information at the beginning and ending of that layer. They have to have an interface to the layers above or below, and as long as we maintain that, we can make sure that our new standard or our modified standard will work with existing technology without a lot of extra mediation that's required. It also fosters competition because products from different vendors can work together. So if somebody's got a really killer layer 2 transition protocol or a layer 5 protocol that kind of fixes a problem that may already exist, that allows them to pull forward in that niche without having to reinvent the entire model top to bottom. This also prevents technology or capability changes in one layer from negatively affecting layers above and below. Now, this doesn't mean that it can't spark change, but it has to be positive change because, again, competition. If somebody fixes something at layer 5 that was a problem, maybe that allows a step in layer 4 or layer 6 to be revisited to process information more effectively. It also provides a common language to describe how networking functions and capabilities can interact. The OSI reference model has 7 layers, and we traditionally read it from the top down, the top being the highest number, because that's the highest level of complexity, all the way down to the physical layer, layer 1, which has the least complexity in terms of the actual data being read. So the application layer contains protocols used for process-to-process communications. So that's a web browser talking to a web server, that sort of thing. The presentation layer deals with common representation of data transferred between application layer services. So we have to be able to package the data in something that's readable. Session provides services to the presentation layer and manages data exchange moving down into transport. So 5, 6, and 7 are often grouped together because their functions intertwine so closely. So the layer 4, transport, deals with services to segment, transfer, and reassemble data for individual communications. This is often where we start breaking data into pieces to make it easier to transport across a network. The network layer provides services to exchange individual pieces of data, so that's the transportation across different physical devices. Layer 2 deals with methods for exchanging frames of data over common media, so being able to send things over fiber optic or copper line. And then physical is the means to activate, deactivate, and maintain a physical connection between network interfaces. So on our computers, if you have a Wi-Fi card, that's going to initiate a connection between itself and your nearest access point. It's going to verify that you have the correct encryption, that you have the correct passphrase, and that your connection is strong enough to sustain transmission. That would be your physical. In the TCP/IP model, we simplify this. We take layers 5, 6, and 7 and convert them to layer 4, application. This represents data to the user with encoding and dialog control. Transport layer supports communication between devices across various networks. The internet layer determines our best path, and network access combines layers 1 and 2, controlling the hardware devices and media that make up the network. So it combines layers 1 and 2 together by eliminating the separation. Now, how can we do this? How can we convert 7 layers into 4 and not violate the rules for the reference model? Well, it's because TCP/IP is specifically what we use for transmission over the internet. We don't have to maintain compatibility with keeping all the layers separate for all of the Novell and Apple and all of those different items. We are focusing specifically on one protocol suite. So we're able to have a specified reference model that condenses some of the material that seems a bit redundant. So here we see kind of a side-by-side comparison of the OSI and TCP/IP models. You can see where I was talking about 1 and 2, as well as 5, 6, and 7 being merged together into simpler layers. So the protocol suite TCP/IP doesn't specify what protocols to use when transmitting over a physical medium in and of itself. So we do have to talk about network and transport being essentially the same, except the network layer just deals with the internet transmission. 3.6, data encapsulation. So segmentation is the process of breaking up a big message into smaller units. And then multiplexing is a related process which takes multiple streams of segmented data and interleaves them together to make the best use of our bandwidth. So segmenting messages has two primary benefits. It increases speed and it increases efficiency. Because we have a piece that may fail here and there, we just have to resubmit the missing piece. We don't have to recreate the entire message, which for certain files would be catastrophic, especially for things like research data. Sequencing messages is the process of numbering the segments that each message needs to be reassembled at the destination. So here we have, a labeling process, and then we can sequence them and send them across so that we say, okay, this is this particular application, this port number, if you will, is requesting this program's information. So we're going to go ahead and send it. We're going to send it piece 1, 2, 3, 4, 5, 6, 7. And another program using a different port would be able to do the same thing so that their message 1 and the message 1 for our machine would not have to cross over, as it were. We are able to identify things based on their physical address for their NIC, their logical address for their IP address, the sequence number for TCP/IP, as well as the port number for the program involved. So that brings us into what's called encapsulation. Encapsulation is just taking a piece of data, breaking it into subsections called segments, adding headers at the various layers as it moves through, and then being able to encode that into bits. So we have what's called a PDU, or protocol data unit, and it generates a header, or in the case of the frame at the last layer before it starts turning into bits, the trailer as well, changing the name of the PDU. So pretty much layers 5 through 7, we have it as just data. When it gets to layer 4, it is a segment. At layer 3, it becomes a packet. And at layer 2, it becomes a frame. At layer 4, where the segment is, that's where we have the port number that identifies which program is doing the requesting for new information or the transmission of reply. The packet attaches the IP address, which does our logical addressing, and the frame does the MAC address, which does our physical interface, our NIC. Once all that information is established, we can then convert it into bits, which can be submitted over the NIC's connection, be it radio frequency, copper, or fiber optic. Encapsulation is a top-down process, meaning that we start at the most complex layer and work our way down until we simplify it down into a stream of bits. De-encapsulation is the inverse of this, where we take the bits information, receive it as a completed frame, and then start stripping off the various headers to get down to the original data payload. So we go from data to the frame, which has our Ethernet information, that's our MAC address. We peel off and get down to a packet. We take the IP address from that, peel that off, get to the TCP segment, strip that down, and then we finally have the user data payload. Now that data payload can be put in place very much like the jigsaw puzzle example I used earlier. Layer 3.7 is all about access. Both layers 2 and 3 deal with addressing to deliver data from the source and destination. So the layer source and destination addresses are dealing with the IP packet moving from its original source to its final destination. That's the network layer. So whenever you hear about layer 3 transitions or layer 3 switches or things like that, you're talking about the network layer. That's IP translation rather than dealing with layer 2 switches, which would be MAC address translation, local traffic only. Data link layer source and destination addresses just deal with moving things from one network interface card to another on the same network. So the IP packet contains two addresses, source and destination. Where did you come from? Where are you going? These addresses can be link local or they can be remote to one another. So here we see a layer 3 IP packet stating that its source IP is 192.168.1.110. Now that is not the public internet address that is available. That is the IP address for the local network that this person's host machine is connected to. We have to have some translation going on at router 1 and router 2 to eventually reach the web server on the opposite side, 172.168.1.99. When it sends it back, it'll use the same path, unless of course one of the links in that path was disrupted, but we'll be able to follow that same information by re-encapsulating so that the response can be de-encapsulated at the opposite side. IP addresses contain both a network portion and a host portion. Now that's IPv4. We can convert that to IPv6 by saying prefix or interface ID. The leftmost part of the address indicates what network a particular frame belongs to. The host portion says what individual host on that particular network is where this thing is going. So the LAN itself will have its own network portion, and the host ID or interface ID will be unique. So those are the two pieces that we look at. Now, when the devices are on the same network, the source and destination will have the same number in the network portion, so we can be sure that we're on the correct network, and then we start comparing the MAC address, so we can see that on the left in the data link frame. So MAC addresses are physically embedded into the NIC. They are not changeable under conventional circumstances. So a NIC has a MAC address that's kind of like the VIN number on your car. It's there when it's manufactured and it stays the same until it's destroyed. On the other hand, your license plate may change based on what state you live in, whether or not your vehicle changes hands, whether or not you get a vanity plate, anything like that. The license plate is still unique, but it's unique to your state, perchance. If you're a Star Wars fan and you get like Red 5 as your license plate, there may be 50 different Red 5s for each U.S. state, but they're all specified by, you know, NC, SC, TX, MA, whatever state you may be in. So again, we have to look at local versus national addressing, same thing as we look at local versus remote network addresses. So what happens when the actual destination, the final destination of transmission, is not on the same LAN and is remote? What happens when PC1 tries to reach the web server through the various transmission methods? How does this impact the network? How does it impact the data link layers? Let's take a look. When a source and destination have different network portions, that means they are not on the same network, which means that there needs to be communication between their default gateways. So we have layer 3 that provides layer 2 with the local default gateway IP address or router address. And that allows it to move outside of its local network to be transitioned into a group of routers, which can then hopefully pass it from one to the next, hopefully the shorter the better, to get to its intended final destination. So we have what's called our DGW, default gateway, that allows us to pass to all other remote locations. And we have to be able to identify, based on both IP address and MAC address, how to transition from one to the other. Data link addressing is local addressing, so once it finally arrives, it is then able to interpret where it's supposed to go. The destination for the MAC address will actually be varied, because it just says, okay, your destination is now 1111111, and then to go to R2, it's going to be 222222222, and eventually it'll get to the MAC address for the local section, ABCDEF 1234556. So let's follow this again. The first segment, going from the source PC to the router, is the destination NIC and source NIC, and it has the source and destination IP address. So as it moves from physical location to physical location, it will peel back that layer 2 information to check layer 3, make sure it's going to the right place. So now, as we're moving from layer 2 to layer 3, the source and destination NIC have to change. The source is the first router, the exit interface, and the destination is the second router that's going to be receiving that information. The IPs, however, are staying the same. This is how we have a verification system moving from one place to another. Lastly, as we're moving from the router that contains our web server to the web server itself, we have that second router's exit interface communicating with the web server's NIC. Once it reaches that connected network, it says, okay, we're on the correct network. Is this the destination IP? Once we verify that, we can deliver the frame. Now, obviously, it takes a long time for human beings to explain how that works. But in the terms of electrical impulses moving through standardized equipment, it's able to be done in milliseconds. So let's notice that the packet, the layer 3 information, is not modified, but the frame at layer 2 is. So we're basically just taking a hop, skip, and a jump going from one place to another, but the original contents of the message beyond the link local stuff on the MAC address layer is not changing. So here are some new terms and commands we looked at for this chapter: encoding, protocol, channel, flow control. Obviously, you guys know how to read, but it just gives you a quick rundown of some things that are considered important for our discussions today. If anybody has any concerns or issues they'd like to address with me, you of course can reach me at my Google Voice number, which is, go ahead and make sure I've got the right one. I don't often call myself, as I'm sure you guys are aware. 910-239-7814. My Cape Fear email is jearmke063@cfcc.edu. And of course, you can message me directly through Blackboard as well for our class. If you have any concerns that need to be done in face-to-face, just go ahead and send me an email or a text and say, hey, Mr. A, I just need to go ahead and grab you during your office hours, and I will certainly be glad to set up a time. Thank you for your time and attention. Appreciate you guys very much, and I will talk to you next class.